Okay, very good, warm and hot afternoon to everyone here. Thank you for making it down to the lecture. This is AA279D, and we're going to be covering topics in relative navigation for distributed space systems today. This is a brief overview of what I'm going to be talking about. I want to try to structure it where it's kind of 50% a review of graduate level navigation topics and another 50% more on what are some of the kind of research and projects that we are doing in the Space Rendezvous Lab. So we'll start with an overview. We'll do a quick review of the Kalman filter. I think Professor D'Amico and some of you are also taking Professor Schweker's class this quarter. You're covering Kalman filters a lot, but we'll still do a quick review anyway. We'll talk about the GNSS measurement models and talk a little bit about IAR in detail. I'm going to start a timer because I have a bad habit of overrunning. So let me just, yes. And then let's look at some formation flying missions that we're pursuing in SLAB, both real flight projects and also projects that we're pursuing with industry. So we tend to think of navigation as a spatial or geolocation kind of problem. Where are you in XYZ? But really, I think let's broaden our minds to accept that navigation can be the estimation of any states. So really what your navigation filter is trying to do is to provide as accurate an estimate of an underlying distribution of some states, given your understanding of system dynamics and your measurement models. And if this is your first time seeing Kalman filters, don't be alarmed because all of us actually practice Kalman filtering on our daily lives, even Doug. So if Doug can do Kalman filtering, so can you. So suppose we have a dog, Doug. He is very ready to estimate when you, his owner, will be coming home. And so he predicts every day, are you coming back home at 6? Are you coming at 5:30? And when he makes these predictions, he is forecasting his knowledge of the dynamics of your return back home into the future until he gets a measurement. And so he hears a sound. Maybe there are squirrels outside. Maybe he hears footsteps. Maybe it's the car key fob making an alarm sound. But it could also be your neighbor's car. It could also be somebody else's footsteps. And so these measurements are also a little bit noisy. So Doug tries to reason with himself, what is the best way to optimally weigh my understanding of when our owner will return home and how noisy or uncertain these measurements are. And if Doug was ever wrong, strictly speaking in the Kalman filter sense, there would be a very large gap between what he predicts and what he actually observes. And so we kind of measure this through something called the prefit residual, which I think Professor D'Amico covered in the last lecture. And so he becomes sad because he becomes more and more uncertain over time about when you, his owner, is coming back home. But if Doug actually models his understanding of when you're coming home accurately, as well as he deepening his understanding of how uncertain these measurements are, he will be more and more certain over time about when you are arriving back home. And so the idea of Kalman filters, really, we try to break it down into two steps. We have the prediction step, which we call the time update, and we have the measurement step, where we actually make the observations and perform the state estimate a posteriori after observing those observations. And predictions are basically transformations. If we have an underlying process and we wish to estimate the distribution of that process, there's nothing in nature that actually says everything that what we are interested in observing has to be Gaussian. We assume Gaussianity thanks to the central limit theorem, and we assume Gaussianity because it's also easy to model. You only need 2 degrees of freedom. You only need the 2 moments to model that distribution. So that's what we tend to do. The true transformation doesn't actually need to be Gaussian. It could be any distribution under the sun, but our understanding of a Gaussian distribution can be transformed. So a multivariate Gaussian distribution can be expressed through your covariance matrix, and a linear transformation would be our best understanding of how, if I have a dynamic process and I have a linearized understanding of that dynamic process, how does it actually propagate over time? More recently, I guess in the last 2 decades, people have been adopting uncentered Kalman filters as well. So uncentered transformations do away with the linearization step. And they say, okay, what are the kinds of how many data points, what are the strategic data points that I want to select so that it preserves all that knowledge of what I need to do to reconstruct my distribution if I were to do some kind of a nonlinear transform on it. And Professor D'Amico covered this in the last lecture. This is just a brief recap on the extended Kalman filter. You have a nonlinear dynamics model, which we call F. And I think I'll dive a little bit deeper into how we actually do this in practice, how we actually compute F and the state transition matrix from F. So we do a prediction of where your state mean is in future. And then we propagate our uncertainty as well based on our understanding of the dynamics. If you are doing some kind of dynamic state noise compensation, in this case we call them empirical accelerations, and I can talk about them more in detail. There's also other processes that you need to handle. Then we do the measurement update. We receive a certain number of measurements, and we update our understanding of what our current state is based on those measurements. In practice, we try, because we are developing flight software for actual space missions, we want to try to be as careful as possible in terms of numerical stability. So over here, the expression for the Kalman filter measurement update may differ a little bit from what you see on Wikipedia or your 273 notes. This is a form called the Joseph form, which basically computes your Kalman gain in a manner where it always preserves positive definiteness in your covariance matrix. So your Kalman gain is computed, and the covariance update happens as a result of instead of substituting the optimality condition, you keep the covariance update in its positive definite form. So this ensures that over time your covariance doesn't actually become non-positive definite. So this is all material that you have already seen in the last lecture and possibly in 273. I know quite a few of you are taking 273 this quarter as well. But let's dive a little bit deeper into how we actually do orbit propagation within a Kalman filter for a distributed space mission or for a space mission in general. Let's call our non-linear dynamics function F. And within F, I have an understanding of how things fly in two-body systems. I have Newton's laws of gravitation. And on top of them, I have an understanding of what the perturbations are. So perturbations, as a reminder, from 279A material, these are things like atmospheric drag, solar radiation pressure, maneuvers even. So they could be self-actuated rather than environmental as well. So you have an understanding of what these perturbations are, and you append them to your understanding of Newton's laws of gravitation. So this is your two-body force with your perturbations. And now for simplicity of just running through how we actually compute the time update, let's assume your variables just position and velocity. So this is a 6x1 vector. So you have r and v at some initial time t0. And you have the differential equation, or rather the rate of change of your state. So the rate of change of position and velocity is basically your velocity and your acceleration. So we define an RK4 integrator. So now we have a dynamics model. We have the dynamics model. We want to start taking finite steps future in time to predict where you are. And there are all kinds of integrators out there. You could do a Simpson's rule. RK4 is generally what textbook everybody uses. There are adaptive step size integrators that you can use as well. So let this just be some generic integrator. And before we actually propagate forward in time, I think one concept that's very important in a filter is time, the notion of time. So where you are right now in time, do you actually have maneuvers that were queued in your software? Did your propulsion queue certain maneuvers for you to do some updates? If so, please handle those maneuvers that are being executed in this time right now. So that's T0 right here, before you actually do your propagation. So you're accounting for them in sort of like an impulse sense. Then once you've accounted for any maneuvers and actuations, you can proceed to do your orbit propagation. So this is just a big overview of how this big function, this nonlinear function f, is being executed. But f only accounts for your state mean. You can choose to propagate your state mean linearly or non-linearly. There isn't actually any restriction. But because your covariance is represented linearly, it's a matrix, you can only propagate your covariance forward using linear operations. So how do you actually run a non-linear dynamics model on your covariance, which is basically a matrix? And so I want to do a quick introduction to the variational equations. I'm not certain if this is the first time you're seeing the variational equations, but Montenbroek in chapter 7 does a very, very good job of proving the variational equations and kind of giving you an intuition for why they are the way they are. But there are 4 main facts that back up the variational equations. First off, what are the variational equations? The variational equations are basically just a way for us to compute what your state transition matrix is. So I know I can compute what f is, right? Like, I have a perturbation model. I have some model that tells me what is the J2 effect on top of 2 body. Now, how do I actually get them into this form? How do I get them into a state transition matrix form? And what the variational equations tells us is there are 4 facts. The first fact is any state transition that has a non-zero time step is just identity. So that sounds like a very obvious fact, but it's actually very important because this is going to be your initial condition. And the second fact that the variational equations states is that, well, this is basically the definition of the state transition. Any state that you have at t0 can be propagated forward in time linearly through the state transition matrix between this time elapsed between t and t0. Now, if I have a linearization of the dynamics, so if I have the Jacobian of my force model, and we can talk a bit about how the Jacobian is being derived later on, then I can actually compute what the rate of change of my state transition matrix is. So how does your state transition matrix vary over time? And this doesn't sound like it makes a lot of sense right now, but it's going to be very useful later on if you want to compute what your state transition matrix is over an arbitrary time interval. So let's do a quick example here. Let's suppose, so this first equation is basically your variational equations. Yes, it's basically this rate of change here. The rate of change of your state transition matrix for the state's position and velocity is equivalent to the Jacobian of your force model multiplied by the state transition matrix itself. So how do we actually get the state transition matrix at some arbitrary t? We know that we have the initial condition. Now we bring in the notion that we have an initial condition, that a state transition matrix between the same time step is basically identity. So that's your initial condition. So if you have an initial condition and you have an ODE, you can do an integral to get what your state transition matrix is going to be in future. But now there's another problem. We broke this problem down into more sub-problems. Now the sub-problem is, great, I have this ODE in this form. What do I do with these components? How do I actually compute what these sub-blocks actually are? And we can get them numerically. We call them finite differencing. I'll skip ahead to the next slide first. And you can always estimate any derivative based on finite differences, right? If you have access to what f is, you know what your force model is. So what happens if you perturb your x position? What is the perturbed effect on your force model when you take the finite difference between your actual original state in position and your position plus some perturbation divided by the interval of like whatever your perturbation interval is. And so this gives you a numerical approximation for what your the sub-blocks of your Jacobians are. And this is what we actually do in practice. We also adopt something called empirical accelerations. And so empirical accelerations are a way of estimating what your dynamics fails to model, what your f function fails to model in the real world, and that is being reflected through how well your predicted trajectories agrees with your measurements over time. And so part of what we do in the state vector is we actually append on top of your positions and velocities, we also append a set of states called the empirical accelerations, and we assume that they follow a first-order Gauss-Markov model. So that just basically means that its current state, the state that it currently has right now, is correlated in time with the previous state, and so there's some kind of a decay model that is associated with it as well. If we append these empirical acceleration terms with your model of just position and velocity, so now you have, so if we look at the full state right now, we have the full state being RV, and we also have the sensitivities with respect to empirical accelerations. Then the full sensitivity matrix, or rather the full state transition matrix, comprises of the finite differences that you have computed, plus the sensitivities with respect to the empirical accelerations as well. The state transitions for the empirical accelerations, because it follows a simple decay model, a first-order Gauss-Markov decay model, the diagonals on it are just simply set as a negatively decaying exponential. But all this said, people have also tried to not worry about the notion of linearization of dynamics. And so one thing you may have encountered is the uncentered Kalman filter, where you don't actually need to worry about the linearization of dynamics, because the uncentered Kalman filter allows you to reconstruct your distribution after a process by selecting five strategic, in this case, because this is a two-dimensional distribution, so they would select 2n plus 1, so this would be 5 strategic points, where post-transformation, you can actually reconstruct your distribution without any approximations or assumptions. And so I've included just the full steps for the uncentered Kalman filter here in this slide, and the slides will be uploaded on Canvas, so in case you want to peruse it. But in the interest of time, this class is not going to go through exactly in details the algorithm for the uncentered Kalman filter. But just know that it exists. So let's review differential GNSS. We've talked about the Kalman filter time update. Hi, Emily. Yes.
Do you ever do a case where you do one part of your Kalman filter with the EKF method, say like your predict step with the EKF, linearized state transition matrix and so forth, and then the measurement update, for instance, with the UKF? Is
Yes.
that sort of a kosher thing to do?
We've done it for digital. So digital is our differential GNSS navigation flight software stack that we have in the Space Rendezvous Lab. In the previous iteration of digital, it used to be an EKF for the time update, followed by the UKF for the measurement update. And the reason is that the UKF generally is better at capturing non-linearities in your processes. At the same time, it is also more computationally expensive, because if you have a very large state, if you're estimating positions, velocities, clock biases, and possibly other environmental parameters, you're going to have a very big state vector. And the number of sigma points that you're going to pick for your UKF scales with 2n plus 1. So you're going to be having many more sigma points to propagate. That and every... it's also not as easy to execute sparse matrix operations in the UKF. But that's besides the point. Yeah, so yes, people do EKF, UKF hybrids. Kind of a balance between capturing of nonlinearities versus computational complexity. I can talk more about the way we are doing it later on. We're doing it in a pure EKF way. Mm-hmm.
an important consideration to make. That depends on the choice of your state representative. So there are trade-offs. And you can make the dynamics much more linear by using orbit elements as a representative. So you don't need an Seneca filter there. So the ECAF does a good job for orbit element state representative. But then the measurement model becomes more linear, more non-linear, in order to go from the orbit elements to, for example, angle measurements, and there you need to capture the non-linearities, and you use the Seneca. So that's one of the reasons why when we optimize really for computational effort, we make that distinction. Here, what Sam is describing is position and velocity. But you can see alternatively orbit elements as your state parameters.
Yep, thank you. All right, do we have any more questions about Kalman filtering in general? It doesn't have to be specific, it could just be general questions as well. If not, let's talk about differential GNSS. And I'm going to focus a bit more on the carrier phase model today. So when your smartphones actually receive signals from GPS satellites, they're receiving, typically there are three observations of interest. Pseudo range is something that is encoded in the signal, and so the range that you're receiving is unambiguous. So you can think of it as very simply, starting a stopwatch on a GPS satellite, starting a stopwatch on your receiver, calculating what is the time elapsed, and based on the speed of light, get your distance, and then also accounting for receiver clock biases and things like that. So that's unambiguous. Your receiver also receives something called carrier phase, which is literally, as we know it, a 0 to 360 degree phase that's part of a continuous wave. The third observation is the Doppler, which gives us the rate of change of your carrier phase measurements. We are most interested, for high precision relative navigation, we are most interested in carrier phase because GPS has these chips. They call these chipping waveforms on the carrier signal that have a rather coarse resolution on the order of meters. Whereas carrier phase, we're looking at a wavelength of 19 centimeters for GPS L1. So if you are 5% off in your carrier phase tracking error, which is very large, by the way, that's like 1 over 20 of 20 centimeters. That's a measurement that has a thermal noise of 1 centimeter. So people are more interested in exploiting carrier phase precisely because the thermal noise in the measurement model is a lot smaller. And there's been a textbook way of how we model carrier phase. This is kind of the agreed upon in literature. Most people adopt this model. So your carrier phase measurement expressed in meters. So this is your actual phase in radians multiplied by the wavelength. So this is in meters. Is basically a measurement of comprising your true range. What is your range between your receiver and a GPS satellite? Any ionospheric delays due to signal propagation delays going through a dispersive media, and tropospheric delays as well, which are not in this equation because we are flying much higher than the troposphere. Then we have to worry about the clocks that are running on your local receiver as well as your GPS satellite. Because in essence, again, if you think about how GPS works, it's measuring ranges just by measuring the time elapsed between the GPS satellite that's transmitting and the time that you record when you receive the signal. And your times are not synchronized with GPS. In reality, they're not perfectly synchronized. So at the very first step, not only do you need to estimate your XYZ, you need to estimate your clock bias. How far off are you from GPS time as well? So this is captured in this term over here. My laser pointer, I don't know if there's parallax. Yes, this term here. And there's also GPS clock biases. So GPS broadcasts its position in space. It broadcasts orbit elements every 30 seconds. And it also tells you what is the jitter about GPS time. And GPS time is maintained by several stations on the Earth. So your signal, or rather the range in your signal is also corrupted by noise on the GPS satellite side. There's something called phase windup, which is an effect when your satellite is rolling in attitude. So if you think that you can imagine that you're tracking a certain signal, and then your spacecraft is kind of rolling. So there's a lever arm motion that contributes to the range as well. But then at the same time, your receiver the phase lock loop is still locked on the same signal, and it's not accounting for the fact that this lever arm is introducing a range bias. So that's called the phase windup. And then we also have this is probably the topic of discussion for a lot of high precision carrier phase differential GNSS-based navigation algorithms, your integer ambiguity. So you can measure phase. You receive a wave that's something between 0 and 360 degrees. But you don't actually know how many wave cycles it has passed. So that conveniently gets lumped into a particular term. We call it integer ambiguity. And of course, finally, we have the thermal noise. So this is kind of the agreed upon model that people use for GPS. And actually for ranging signals in general that pass through the atmosphere, people tend to adopt a model that looks something like this. How good am I on time? Okay. And here's something that's very interesting that geodesists found out a long time ago when they were doing land surveys. If you take the difference of two, we call them zero difference carrier phase models, or zero difference carrier phase measurements, if you take the difference between two measurements, actually some of those error sources are highly correlated. So especially if you have a short baseline between A and B, where the signal ray trace goes through the same path along the ionosphere. And so what happens is, you realize that the ionosphere, more or less over the same locality, provides a kind of similar delay onto the measurements of whatever A is receiving and whatever carrier phase measurements B is receiving. At the same time, they are also receiving from the same, for a single measurement, from a single GPS satellite measurement, it's a common source. And so these GPS satellite errors are also correlated because they come from the common source. If their attitudes are also in sync, which usually in a formation flying mission, we try not to let another spacecraft tumble out of control while the other is nominally in a good attitude profile, this also is a highly correlated error. And so what happens is if A communicates to B what its measurements were, its carrier phase measurements were from the GPS satellite, and it takes the difference between them, right? Several of these error terms go away. So now what we have, notation-wise, I've added something like a delta here to indicate that this is a differential measurement. And what you have right now is a single difference carrier phase model that actually is corrupted only by differential receiver clock biases, so the differences between both of their clock biases, and a single difference integer ambiguity. So what is the difference in ambiguous cycles between this signal pathway and this signal pathway? So how useful could that be? It turns out very useful because with some linear algebra, you can actually reconstruct what your relative position is. So notice on this measurement model here, I have an observation and I am able to relate what my differential range is based on this decomposition. So if they're close enough, if the baseline is close enough, and these two signal ray traces are almost parallel, you can construct a right-angled triangle here where the unit direction vector to the GPS satellite that is common to both A and B, they are actually useful for computing what your baseline AB is, because this is just a projection, right? Vector AB projected onto the unit direction vector would give you what your single difference range measurements are. But there's not just one GPS satellite in space. You're receiving from 10, 12 GPS satellites. And so what happens is you can group all of these measurements. You can group let's say you have 10 GPS satellites in view and you've communicated 10 measurements across each other, you can group your geometry terms on the right side and your observations minus uncertainty sources on the left side. Is it your left? Yes, it's your left. And so you can stack each of these equations and basically get an AX equals to B kind of problem. So 10 satellites, you would have a B that's a vector of size 10 and X that's a vector of size 3. So I'm not accounting for clock biases yet. And you have a geometry matrix that basically is a 10 by 3 in the case where you have 10 single difference carrier phase measurements. Now you can solve this in least squares. This is your classic AX equals B problem, but except you don't actually know what your differential single difference receiver clock biases are, and you also do not know what your float ambiguities, your single difference float ambiguities are. So there's one impediment to you solving this AX equals to B problem. One way to, before we talk about double differencing, one way we can do this is to take these terms out and actively estimate them in the Kalman filter. So if you have sufficient measurements, because these are just biases, if you have sufficient measurements and you have a good understanding of the dynamics, your filter would be able to converge and guess what are the bias terms that best explain your observations. So some people take it a step further. They do something called double differencing, which is, now I have a single difference measurement for a single GPS satellite between two receivers. What happens if I take the difference between a set of single difference measurements? So we're talking about the baseline AB with the transmitting source P and the baseline AB with the transmitting source Q. What happens if we take the double difference of that? And because we are looking at the same two receivers, this single difference receiver clock offset is also common. And so this gets canceled out as well if you take the difference between one single difference carrier phase measurement and another. Now your double difference model has, and this is denoted by a nabla delta, you have a double difference measurement that is just a linear combination of your observations. They're like readings that you readily can access. And you realize that the only nuisance parameter that you don't know offhand is this double difference integer ambiguity. Similar to the single difference case, you can estimate what the baseline is through some clever geometry, because now they're just two right-angled triangles, each where the base of each right-angled triangle is the unit direction to a particular GPS satellite. So you can do this AX equals to B setup again, where if you have your measurements and if you could estimate what your double differenced float ambiguities are as part of your state vector in your Kalman filter, then you have all the information on the right-hand side in order to solve the left-hand side, given sufficient measurements. So this is just the same setup as before. This is AX equals to B, with the caveat that now you have removed your single differenced receiver clock offsets. So let's talk about integer ambiguity resolution. And what's the link here? The link here is that when your Kalman filter doesn't work on, well, the naive Kalman filter that we are familiar with works on floating point numbers. In reality, these are integer numbers of ambiguous cycles. So these are actually integers. We estimate them as floats. And so if we really want to milk out that precision from the measurement, we need to be able to guess exactly how many integer wave cycles there are. And so this is what the IAR, or integer ambiguity resolution block, does. We've done the double differencing. The next step is to do a decorrelation before we do a discrete search. So this is just an optimizer. We validate the confidence of our solution. And if they are confident enough, we say we fix the floats to integers, and we update what our knowledge of these float ambiguities are into integers. So we talked about double differencing. This is in essence just to familiarize yourself with the kind of the typical format that literature tries to adopt. So literature usually gives double differencing as like a nabla delta. Single differences are a single delta here. Subscripts are your receiver indices, and superscripts are your GPS satellite indices. You can actually perform your double differences using a transformation matrix, because if you notice this equation, this is a linear equation, and if you have 11 single difference carrier phase measurements, you can pick one as the reference that you're going to subtract, and that would be your reference that you would deduct away from your double difference model. So from 11 single difference carrier phase measurements, you pick one as the reference to subtract. Now you're left with 10 double difference measurements in total, 10 independent double difference measurements, right? Because if the reference subtracts itself would just be 0, so that you would have 10 double difference measurements. And you can do this with a transformation matrix that's n by n minus 1. Similarly, this transformation matrix can apply as well to the covariance. So if you're estimating single difference ambiguities or double difference ambiguities, you would have access to their covariances as well as part of the Kalman filter. You can apply the same transformation to convert a single difference float ambiguity covariance to a double difference float ambiguity covariance using the similarity transform. So this is the core of how IAR actually works. This is the decorrelation step. The idea is that because all of my double difference measurements are basically made by taking single difference measurements minus a reference single difference measurement, they're all correlated to some extent because it's subtracting from a common measurement. And the reason why we want to decorrelate them is because the covariance gives us kind of a measure of the confidence space of what these integers are. And so we do something called an LDL decomposition, where ideally an LDL decomposition would be able to give us a much more circular, less elliptical covariance, because it's brought out the eigenbasis. And if you plot the geometry of just a diagonal matrix, that's a perfect circle. But there is a seminal technique called the Z-transform in literature, where it's basically an LDL decomposition, except it accounts for the fact that I'm dealing with integers and not floats. And so it does an LDL decomposition where the Z-transform is an integer approximation of the LDL decomposition. So this is a little bit deep, and I'm not going to dive into the specifics of this. Actually, let me see how well I'm doing on time. Okay, yeah. But essentially, what we want to achieve is we want to know what is the basis that we can transform our uncertainty into a space that is very as spherical as possible. And the approximation sign comes because we are imposing integer constraints in the Z transform. When the optimizer actually begins, we need to demarcate a search space for the optimizer, because we're not dealing with floats. This is a discrete optimization. So we're searching over a discrete search space. We need an initial guess. And so what we have is something called integer bootstrapping, which is just saying what the rounded float integers would be, but conditioned on prior rounded float integers. So if I'm estimating 10 float ambiguities, a very naive way to come up with an initial guess is to say, hey, I could just round all of them to the closest integer. That would be like the most naive way to do it. But because I actually know what is the statistical relationship between each float ambiguity, I know their covariance, I know the correlations. And so I don't know if you're familiar with the notion of conditional expectation. And so really what a conditional rounding is I'm rounding the most confident integer, the most confident float that I'm estimating. This is the one that has the smallest variance along its diagonal. This is the one that I'm most confident, based on my Kalman filter's estimate of the covariance, would be an integer. I round this, no other conditions. My second integer would be what would be the rounding of this integer conditioned on the fact that I have rounded the previous one. And since the correlations are captured in the covariance matrix, you can compute this conditional expectation explicitly. So again, because this is not a statistics class, I'm not expecting everyone in the room to be familiar with how conditional expectations are being computed. But at the end of the day, we are computing an initial guess for where to start the optimization. And then from there, the initial guess scaled with the initial guess minus your best float estimate, and then scaled based on the Mahalanobis distance of your, which takes as the matrix argument your covariance inverse, in other words, your confidence, gives you kind of a search space. And so I'll have a diagram to show exactly how we do this in the flight software. But then once we are in this decorrelated search space, we do a discrete step around and search for integers. So no gradient descent, no continuous methods. This is just discrete searching within a search space that you have already decorrelated and have made easy to search without running into dead ends. Yes?
Could you explain the Z transform again? Like, I guess in the previous slide.
Yeah, so the LDL decomposition, if I was interested in finding out what the optimal float ambiguity is, that would just be what I already have in my Kalman filter, right? Because my Kalman filter, ideally, if I design it well, it will converge to the optimal solution. Before talking about the Z transform, let's talk a little bit about this diagonal matrix. The algorithm that was proposed says that because, maybe it's easier if I just jump several slides ahead to, okay. So this is your covariance. This is your covariance of your double difference carrier phase measurements. It's very elongated because it has a lot of correlations with your reference single difference measurement. And what the LDL decomposition does is it shrinks, or rather makes it less elongated, so that if you notice, just like visually, these discrete points here, these are your integer, so for a dimension of 2, right? You want to do an integer search over your confidence interval. It's very hard to, or rather it's very inefficient, and you might get stuck in like a dead end if you have a very long kind of confidence interval. And so what the LDL decomposition does is it will shrink it into a perfect circle, ideally. But it can't be a perfect circle because what the Z transform actually imposes is an LDL decomposition where your transformation of your float ambiguities preserves the integer form. Yeah, it's very involved, and I would suggest that there's like a 20-page paper that explains what the Z transform is. So it's very difficult to explain it in just one lecture, but the idea is that you want to preserve the integer constraint in your distribution. So if you treat these just as pure floating point numbers, a perfect LDL decomposition would just give you a perfect sphere. If you consider the fact that there are integer constraints in your covariance matrix, then it's not going to be, it will be as close to a sphere as the integer constraints get. So that's kind of like the high-level explanation for the Z transform.
It's a change of variable. When you move from your float ambiguities to Z, can you find that transformation to make it simple? So that's the intuition.
Yes.
Okay.
And then you solve a problem in Z where there is no correlation anymore.
Yes.
So say a change of variable. You have to think of it as a change of variable.
So the elongated is Q, and then normally the pure circle would be the D diagonal
Yes.
one, but then with the Z transform, it's like
It's going
Close to
to be,
circular,
it's
but not
close to
exactly.
circular. That's kind of the idea. And again, the stepping back, like looking at ellipses and circles, the big picture idea is that your covariance gives us a measure of your confidence intervals. These are your confidence ellipses. And you want to be able to search around regions where you're most confident of what your most likely integer candidate is going to be. But that's a great question. Okay, so let me step back. Yeah, I think I spent too much time on IAR. Yes. So in the last step, we just want to make sure that we don't accept any integer that we search for. Authors in literature have proposed, especially there's a giant in the field of IAR, Professor Peter Tunison, proposes, and he's the person that came up with this algorithm, by the way, proposes also statistical tests that you can conduct to validate your probability of success in closed form. And also something called a discrimination test. I have to admit, I'm not particularly well versed with the intuition of the discrimination test, but my best understanding is that you want to be able to see variability in your two best integer candidates. So it's kind of like a check where if your two best integer candidates are too far apart, that means something is wrong. At the same time, if it's too close, or if they are the exact same candidates, then something went wrong in your algorithm as well. That's my best understanding of what the discrimination test is. Yes, so let's relate all of this material with, am I good on time? Half time, okay, good. Let's relate all of this to 279D stuff, formation flying, different distributed space systems. And we are seeing a lot of increasing adoption in carrier phase differential GNSS for formation flying missions. And in fact, probably the most prolific one that is old but not that old is the GRACE mission, which I think Professor D'Amico has had the privilege of working on the ADCS system for the GRACE mission. So GRACE at the time had bespoke GPS receivers, but the processing ability was not high enough to do onboard Kalman filtering with IAR. So what they actually did was pipe down all the measurements on the ground and do batch least squares post-processing to solve for the double difference integer ambiguity. So that's just AX equals to B, but a giant AX equals to B matrix just after dumping orbits after orbits of GNSS measurements. Then Terasar X and Tandem X, which is responsible for the most accurate digital elevation model of our time, and I think Professor D'Amico has also had his hands on this project, attempted the same thing while doing very precise frozen repeat ground track orbit maintenance. So they actually use CDGNSS to maintain the baseline about a 500-meter interval, so you can think about the trajectory as like a tube, and another spacecraft is just kind of following around it in an ellipse. So I think Terasar X and Tandem X was an INSAR project. At the same time, they also did some digital elevation modeling. And of course, we have the PRISMA project, which was Professor D'Amico's PhD work. And this was the actual first mission that estimated float ambiguities, differential float ambiguities, single difference float ambiguities online in real time. And PRISMA was actually able to attain relative positioning accuracies of about 5 centimeters and less, and relative velocity errors in the sub-millimeter per second scale. But PRISMA did not have IAR on board at the time due to computational constraints. This is what we are also trying to achieve in VISERS as a next step. So this is a broad overview of the kind of flight architectures that how we actually execute and actualize a carrier phase differential GNSS implementation on flight software. Broadly speaking, in most literature, most CubeSat projects that do use carrier phase differential GNSS adopt a similar architecture, with the exception that so far none in flight have attempted IAR yet. And that's where we are hoping to be the first, at least for the CubeSat class, at least that's what's disclosed in open literature, to attempt IAR. So you have a data interface that does the exchange of the measurements that are necessary, as well as auxiliary information such as maneuvers, attitude, and non-GNSS measurements as well. If you're doing some kind of sensor fusion, or if you are doing some kind of alignment verification, which we're going to talk about in visors. And this is all basically just a Kalman filter. This is, this at the heart of it is a Kalman filter that estimates a set of states. For brevity, I'm not going to share what the states are until the next slide. But I'm going to talk a little bit about the data interface. So the actualization of interfacing is actually quite precarious because you're dealing with a lot of hardware sources that are running on their own threads, on their own, and they have their own onboard clocks and things like that. So the data interface has a key responsibility. It receives a bunch of necessary information to perform differential GNSS. They may not necessarily come in, they'll come in order within their own subsystems, but they may be running on different timescales, and we're not guaranteed that they will arrive overall in time order. So the interface actually helps to sort out what these timestamps of these packets are, and it also is responsible for triggering an emission of crosslink over to the other spacecraft. Because remember that in differential GNSS, its neighbor needs to know what its measurements are so that they can do the error cancellations. In digital, which is what we call our carrier phase differential GNSS flight software, it stands for the Distributed Multi-GNSS Timing and Localization Flight Software. Digital, by default, estimates the following set of states. There are positions, velocities, empirical accelerations, which I talked about very, very briefly at the start, your receiver clock biases for a single spacecraft. Then this is repeated again for a second spacecraft, a deputy. And again, there's no limits to putting a third spacecraft here as well. So this is just a two spacecraft example. Then we also estimate what the undifferenced ambiguities are and the single differenced ambiguities observed, estimated as part of the state. This is just a reductionist diagram of the interface. But really, all of these measurements and auxiliary data come together to perform the high fidelity orbit propagation. So this is the function f that was at the start of this presentation, and a linear covariance propagation. We perform absolute ranging for absolute state estimation, and we do single difference carrier phase measurements. We use single difference carrier phase measurements for relative state estimation. So that's computing the baseline between your two receivers. This external block is kind of a bit more researchy. It's, we have been trying to experiment with ways to do sensor fusion. So we have left this function available as well for the Kalman filter to ingest additional measurements. We've recently also started doing some work on fault detection, isolation, and recovery. And this is, of course, the integer ambiguity resolution block that we talked about earlier. So we've talked about this. This is just how the sequence of software executions that actually happens in the flight. We start with our estimates of the single difference ambiguities, which come from our state vector. We double difference them. We decorrelate them using the Z transform. We do the conditional rounding first. That gives us both the initial guess as well as a scale for our search width. Then we begin searching and evaluating discretely what the optimal candidates are, and we continuously repeat the search until we have the two most optimal integer candidates. We pass them through a set of statistical tests, and we convert them back into single differenced. So because they were double difference here, and our state vector deals with single differenced integer ambiguities, we resolve them back and plug them back into the state vector. Yes?
I think in one of the slides it was mentioned, maybe I'm mistaken, that the integer ambiguity resolution is done off-board, so it's
Yes.
like streamed down. What is the calculation here that's most intensive that requires you to do it off-board instead of on-board?
It's a good question. Ironically, we found out that integer ambiguity resolution isn't any more computationally expensive than a Kalman filter update if the computational steps are designed well. So there's some kind of sparsity optimization and things like that. The key impediment was that at the start, when you have 12 to 16 GPS satellites in view, you have a very large state vector, right, of single difference ambiguities. You are looking at like a 10-dimensional ellipsoid as a search space. So you can imagine that if your confidence interval was, I don't know, for example, let's say it's 5 integers in width. Now, if you scale that by 10 dimensions, it's actually it's not a trivial optimization problem, or rather, it would take a fairly long amount of time on the first fix. The good news is that generally, once your first batch of integers get fixed, any new measurements that come in or any new GPS satellites that get tracked, they show up as a new unresolved integer. And so if they're coming in sequentially, you're only dealing with just one at a time. So the impediment is really the very first step where you have a very large dimensional search space. Once you've resolved that and your filter has converged, yes?
I'd like to make a couple of considerations. First of all, you implement something on a space only if it's required. And so on missions such as Grace, TandemX, Prisma, there was no such requirement of achieving millimeter accurate relative position knowledge. So that's the first reason why this was not pursued on those missions, because it was not required. The requirement for Grace and TandemX to do millimeter accurate relative position estimation was on the ground to process the synthetic aperture radar data or the accelerometer data of Grace, so to generate a science product that doesn't need to be generated in real time on board. This is done offline over a long period of time using data that are downloaded from the mission. It would be reckless to implement something of that complexity on a spacecraft if it's not required. Second, complexity. There is a huge amount of bookkeeping to do integer ambiguity resolution. And robustness. Notoriously, integer ambiguity resolution is not robust. And so if there are mistakes, you make mistakes in fixing some of these integers and you send them back to the state, then it's a potential divergence of the field. So robustness is really a key factor that intimidates us to implement that. So one question would be how are we treating robustness, for example, for the Visor's mission or later for study. These are missions where instead that level of accuracy is required on board and where we need to do integer ambiguity resolution online. And so it would be interesting to understand, okay, how can we increase robustness in order to accomplish more?
Yeah, so in 2005, there was a paper by a lady, Sandra Verhagen, that talks about the open problem of ensuring your integers are correctly fixed. And I think as far as today counts, it's still an open problem. There still hasn't been any algorithms that give very rigorous guarantees. You can give statistical guarantees, you can give a probability of successful integer resolution. There isn't, like, in the way we think of like something that's asymptotic convergence, there's no mathematical guarantees for whether something is correctly integer fixed or not. So far, we only have statistical tools to help us. All right. Do we have any more questions in the meantime, since we are kind of in a Q&A mode right now? All good? Okay.
What happens if you get money?
It's a great question.
Do you have some Someone's asked to show.
Don't, but what I can share is that if you get one integer wrong, if you notice what happens, this line here, it says, once you resolve your integers, your confidence, or rather your uncertainty goes to 0. That means you are very, very confident that this float ambiguity corresponds to this integer. So what happens if you're wrong? Your filter is going to be extremely confident that the choice of your integer you picked is correct, and it's going to force your state estimate to obey that integer that it thinks it should be. And so everything else in your state vector has a non-zero covariance. Everything else has some level of uncertainty, but now your filter is saying, no, I fixed this. This is definitely this integer. In reality, if the filter is wrong, it will force all of the other states to compensate for it. This is actually partially mitigated in digital because we are estimating many bias terms. And so one thing throughout the process of developing this software, one thing I have noticed is if you do get one integer fix wrong, the software responds by fixing all of the integers wrong by 1, and then scaling back the bias terms by an equivalent negative amount to compensate for that. So I have seen that happen. That's just a hypothesis. I'm not very, very sure if that's actually what's happening. But basically, the key big picture idea is that once you have a confidence or an uncertainty of 0, your filter is going to treat that state as a forcing state on the rest of your state parameters. And you will see undefined or unpredictable behaviors happen. So in general, it's disastrous to have a bad integer fix.
Sorry to ask you a question. But
No, you're not.
The Q setting it to 0, if we have some statistical guarantee that the integer is correct, to say like 95% guarantee, then why don't we set the Q equivalently, like 0.05?
Yeah, that's a great question. The idea is that as long as so Kalman filters in general have some steady state performance, right? If it converges over time to that steady state performance, and let's say you modify this algorithm and you fix this, but you say, no, I'm going to give it some non-zero uncertainty, what's going to happen is it's just going to revert back to its steady state performance. So chances are, and my prediction is, if this was non-zero, eventually over time, this will converge back to the original covariance values that are in your float ambiguities. Mm-hmm. Yeah.
So let's say at a single time step, you're off in your integer by 1. So that corresponds to like a 19 centimeter error in your measurement.
Yes.
Is there robustness built within digital at the next time step when you're back to having your integers resolved well? Is there robustness built in to correct for that error and come back to the correct state? Or how does that work?
Do you mean robustness after you have integer fixed?
Yeah.
Currently, no. If you have integer fixed, you have committed to these integers. There is no feature that allows you to backtrack and say, maybe I don't want to work with this integer anymore. We could implement something like that because if you do see a 19 centimeter spike in your residuals after you integer fix, chances are you fixed a bad integer. So that could be an indication for your software to say, maybe let's take a step back and not be too hasty. So that's a good suggestion. Thank you. All right, let's move on. Okay. So where are we right now in digital? We are currently at a stage in Visors where we're doing a lot of validation and testing of our flight software. We are also dealing with a lot of uncertainty modeling. We want to be very sure that the flight software has very good knowledge of where all sources of uncertainty are. So not just the measurements, but the dynamics and also even contributions by body frame uncertainties. And so at the end of the day, a GPS receiver always receives measurements from a GPS antenna. but your positions and velocities may not necessarily correspond to that GPS antenna position in the body frame. So there is a bias effect in your measurement if you rely on some static predetermined center of mass to phase center offset. And so we try to capture this in our Kalman filter design by doing what we call a sparse and stable consider extended Kalman filter. In summary, it's basically just considering the uncertainty influences of, say, center of mass uncertainties, phase center offset uncertainties, and we are trying to compensate for that as well within our filter by propagating those influences into our state covariance. Again, because we are preparing for flight, a lot of the algorithms that we develop have to be computationally stable. Numerical instability issues cannot arise because if you run into a singularity in flight, your software will crash and your satellites may be in an undefined state. So you will have a dedicated lecture on the Visor's mission, but in the interest of just sharing the context with you on what we're developing for the navigation software, this is just a brief overview of what Visors is. It is a distributed space telescope. Think of it as flying a camera in space, but you are segmenting the optics component away from the detector housing. And so what we want to achieve is instead of telescopy using bus-sized telescopes like Hubble, you can achieve the same kind of resolution and focal length using smaller miniaturized distributed satellites. And this is just a video that I prepared for the Visor's mission. I'm not sure if you've seen this video, but I like it. It's made of SDK. So Visors flies in a sun-synchronous low Earth orbit, 500 kilometers. This may change depending on launch manifest details. But essentially, we start at a 200-meter baseline in what we call standby relative orbit. And one of the spacecraft, the maneuvering spacecraft, successively applies maneuvers in steps of 2 millimeter per second impulse bits until it gets into a desired science relative orbit, which has a baseline of about 40 meters. And so the relative orbit design, I didn't come up with this. This has been passed down by generations of students. I think since Professor D'Amico's first PhD student has been working on the relative orbit design, the mission design for this. But the design of the relative orbit is such that at opportunities of alignment, the angular displacement between the optic spacecraft and the detector spacecraft matches the beta angle to the sun as measured from the tangential axis, or rather, in this case, that's RTNY. Every science campaign, there's one observation attempt or one alignment attempt, and in total, there are 10 science orbits. Yes.
There is a guaranteed distance in the array.
Yes. So I'll show you in the plots later, but there is a very specific EI vector separation that is applied in order to achieve a passive RN safety ellipse. And it's not so clear because this is a 3D motion projected on a 2D screen, but I'll have a projected plot that can show that RN separation in the next slide. And by the way, the soundtrack comes from Galactic Civilizations. It's a great game. You should play it. All right. Just some current measurement performances based on the current state of the software that we are in right now. This is a campaign where we do a role switch. We have one spacecraft perform maneuvers at the start. So these red translucent lines are maneuvers. And we do a role switch midway into the campaign. We have the other spacecraft. So we do a kind of a handshake, and we have the other spacecraft play the role of the maneuvering spacecraft. We check that the navigation flight software is able to receive these and include them as part of the orbit, the time update step. We also have a laser rangefinder on board Visors. We use them as an alignment verification tool. Oh, sorry, did you have a question? Oh, okay. Sorry. From the corner of my eye, I saw someone raising their hands. Yes, so we use it for alignment verification, but we also have the option of using it for sensor fusion, although at this moment I think we're not doing it right now. And this is a modeled scatter grouping of the laser rangefinder readings on the detector panel of visors. The grouping is about plus minus 2.5 to 3.5 centimeters in the semi-axis of the ellipse. And this was the this is the result of the very specific EI vector separation that Professor D'Amico was talking about. It's chosen such that during science, if you notice, there is an RN separation of about 5 meters in RN separation here. There's also a long track separation, but this doesn't guarantee passive safety because in the long track you may drift due to differences in your atmospheric drag. But yes, this is just an overlay of what the ground truth trajectory is with your state estimates trajectories. And this is the sun. The sun, I probably forgot to mention this, which is probably the most important thing, but the science mission is to image the sun of all the things. We have also tried running digital, at least software in the loop, for a rendezvous and proximity operations scenario with, this is with Blue Origin. So we have also galactic civilizations. We have I think this is it's one of the ESA spacecrafts. I forgot what it's called. Automated Transfer Vehicle? Yes, I think it's the ATV, yeah. And so we simulated a trajectory for them, and we included the effects of multipath noise, which is a very simplified model for multipath noise, for a single rendezvous and proximity attempt demonstration. All right. In which this rendezvous demonstration took about 5 to 6 hours, so it was about close to about 4 orbits maybe. And the docking point was not at 0 because the ISS was actually pretty big. So if I manually computed what the docking point would be, and I just set that as the rendezvous point. And this was just running digital statistics to see that, it could actually perform moderately well under the influence of multipath noise as well. There has also been interest in SLAB to do integrated navigation, so fusion of carrier phase differential GNSS with range measurements. This could come from the crosslink, or this could come from a dedicated device like a laser rangefinder. It could also be from camera models where we use azimuth and elevation. So this is angles-only navigation from analogous to the Starlink mission, which I think Justin will be sharing with you in the subsequent week or two. And we've had this big endeavor, I think, early last year, where we tried to integrate all of our software efforts into this toolbox called the RPO Kit. Essentially, it is the vision-based navigation flight software stack with our differential GNSS software stack and the IAR block fused together in a common framework. And why do we want to do this? Because differential GNSS assumes that your other remote spacecraft is cooperative, that it can communicate its measurements with you. Operationally, that is not guaranteed. But one thing for sure is that if you can see a spacecraft within the field of view of your camera, it matters not whether it is a communicatable spacecraft or not. So by fusing angles only, range measurements, and differential GNSS, you're actually widening the scope of operations that your flight software can handle. And so not diving into details here because there's just a lot going on, but essentially these are all of the external subsystems that provide software emulated packets to the flight software. These are the data packets that we're interested in, and this is the integrated navigation stack that we have attempted to build. We have kind of demonstrated some inspection and rendezvous type scenarios between close and far range. So this is one of the scenarios where it does an approach and then it does a very close range rendezvous, and then it departs and goes back to its original waypoint. And you may be familiar with these are the ROE plots. And for a close range, for a close approach scenario as well, where the scale is down to about 100 meters or less, we also similarly perform an approach, close approach, and inspection. Both of these this is running digital and angles-only navigation, which we call the Artemis flight software, together at the same time in the same common filter. Some other interesting research topics that we've kind of looked at, we know we are gearing up towards performing IAR in low Earth orbit. We get pretty good GPS coverage. We can see about 12 satellites nominally at any point in time. But there's been growing interest of using side lobe signals for GNSS. So these are signals that are not on the main lobe. You are actually not under the main lobe of the GPS satellite. You could be on the side lobe. And that means that your area of operations can be extended from low Earth orbit all the way to GEO. So you could fly higher than the GNSS or GPS constellation, and you may still be able to receive side lobe signals. And I think there was some news recently that an Italian company called Fugro, I think one of their payloads was a GNSS receiver that was flown to the moon, and they were actually able to carrier track signals, GPS signals on the moon. So there's some promise here. We did do some preliminary analysis, at least at a level that is accurately reflective of the kind of thermal noise that your receiver would be observing if you're flying in geostationary orbits. So you're flying higher than a GPS satellite. And the key idea is, if we want to enable high precision operations in a higher orbit, how do we achieve that? And the idea was to still perform float ambiguity estimation in real time on your filter, but then you have your angles only and range measurements form an additional constraint on your IAR process. So this is just a snapshot from a paper that we did where I showed that this is basically a contour plot of like the cost function, and so there's a cost minima here without the angles only constraint. So this is just based on the current set of float ambiguity estimates at filter convergence. And if I were to integer resolve naively just by rounding, I would round it off on the wrong integer. But if I actually included the constraints, the cost curve the discrete cost curve actually shifts where the minima is much closer to the actual true integer value. So this kind of just a broad idea. Every GPS satellite is sending you a bunch of signals, and you're really trying to estimate what the differential number of wave cycles are. So these are just wave fronts. So the number of wave cycles will be your undifferenced number of ambiguities, and your single difference ones will be taking like the difference between 1 and 3 or 2 and 3, etc. Your angles only measurements, the question was whether we could use angles only as a means to constrain what your integer search space is, and whether we can also use range measurements to constrain what your search space is. And we found that actually, yes, it does improve on your performance pretty well. Not going to run into details because we're running low on running short on time. But there I have a video. I didn't realize I put a video. Okay. This is a geostationary orbit. So you can see you're flying much higher than the GPS constellation right now. And I've modeled the thermal noise to mirror what you would get if you were to receive a carrier-to-noise ratio at geostationary orbit. And you can see that even in GEO, you're still getting pretty good side lobe coverage. This assumes that you're tracking all the satellites that are within the elevation mask of its transmitting signal, which is a big assumption, but if that assumption is correct, we actually could achieve IAR at 400 minutes. What's 400 minutes? 7 hours? We could actually achieve IAR about 7 hours into the actual operation. So we're actually fixing integers in geostationary orbit. And so we're looking at, the scale is very big because everything is very noisy in geostationary. The gray plots are what your performance would be if you were just navigating relative navigation based on your side lobe signals. And the colored plots are what happens once you start including range and angles only measurements in your Kalman filter and also including them in your IAR constraints. So some final thoughts. Rigorous filter design, documentation, and testing is really key to any navigation operation. So a lot of navigation algorithms stay on paper until they actually get rigorously tested for flight. And that is the big step that makes anything flight ready. So establishing that fidelity has been the core of what we are trying to do at SLAB. Second point, carrier phase differential GNSS with IR is established, but we hope to be the first to exercise IAR, flight test and flight validate IAR in orbit, at least on a CubeSat class mission. Sensor fusion has also proven to be a pretty interesting research topic that can extend the robustness and also area of operations or concept of operations for distributed space systems. If anybody's interested in pursuing like a PhD in this topic, it's always growing because GNSS standards, GNSS architectures are also always growing. There's a new block, GPS Block 3 has been launched. Galileo, QZSS is always launching new precise products in real time. There's a lot of interesting research topics that students can pursue for their PhD with regards to GNSS, not just for formation flying, but just in general. So that includes things like Jodeci as well. And finally, just an acknowledgement that while I am presenting, digital was actually a team effort. This whole navigation endeavor started with Professor D'Amico's PhD thesis, and Vince Girallo was the student that worked on CDGNSS while he was in SLAB before it was handed over to Toby and me, who are now both actively working on a navigation flight software stack in VISUS. And of course, it's not a silo. This is an ecosystem where everybody's working in tandem together and everybody's in a good collaborative spirit. So thanks to everybody else in SLAB as well. Exactly, 1 hour, 20 minutes. Okay, thank you. Okay, do we have any questions? Yes.
Quick question. So I think Proba 3 just launched and they're claiming that millimeter level accuracy. If they're not doing IR, what other sensors could they be leveraging in order to get that level of accuracy, if you know?
Yeah, that's a good question. So Proba 3 is using differential GNSS when it's in perigee. So for context, Proba 3 flies in a, maybe let's use Vince as the Earth. So Proba 3 flies in a highly elliptical orbit. And at the apogee, it is much higher than where the GNSS satellites are. At perigee, it is doing relative navigation, but I don't think they're doing IAR, right, Professor?
They're using basically the algorithms I developed for the Prisma mission.
Yes.
I contributed to the phase A and B of Proba 3, and I demonstrated that you can achieve centimeter accurate relative positioning during the perigee arc.
Yeah.
And then you are dead reckoning, you are in propagation only mode from after the perigee all the way to the apogee. And that the accuracy you get up there is about 10 meters, 15 meters from that propagation, from the very up. And it's enough to lock the laser metrology. And that's the precise metrology they use in order to align with the millimeter accuracy.
They have some sort of laser to
Angles
do.
only navigation. It's a combination of angles only and laser metrology.
Yeah. So I think they have a beam position sensor that they use at observation, and also like a shadow cone sensor to probably some centroiding. And then the solution from orbit prediction from perigee is enough to initialize the filter with the new sensors once it's at observation. That's my best understanding.
It's a combination of GPS and vision based in different phases of the orbit.
Yeah, that's cool.
All right. Do you have any more questions? If not, you know where to reach me on email if you have questions. I'll be more than happy to take any thoughts, comments, and etc. And thank you.